Good job. You're chairing the session, right? There you go. Yes. But it says on our schedule. Morning. How are you? Good. And yourself? Good. Fine. Good. I've had worse. Yeah. So, liaison. She can hear us.
Yes, I can hear you.
Awesome. Can I just make one little announcement before we start? People. Good morning.
Good morning.
Yeah, let's try that again. I know there are still people on my way, but they are coming. Let's try it again. Good morning.
Good morning.
Thank you. All right, last day. I hope everybody had fun last night. Those of you who came. It was a blast. I'm super proud of it. It was worth it. All right, last day. If you happen to leave before the end and you want to return the plastic thing that your badge is in, there's a box on the table in front of Frank. And you know, they reuse them. So if you want to be environmentally conscious, then do that. And I think with that, I will turn things over to Joel to kick off our last day.
Morning, everyone. Morning. Good morning, Joe. Morning, Joe. Okay. So welcome to before that. I'm Joel. I'm also Hawaii. Put that out of the way. Welcome to the penultimate session on black holes and accretion. Our first speaker will be Leah about talking to us about the millimeter axis in RQ and AGN with multi-zone notebooks. You want to share your screen?
All right, this is me, right?
Yeah.
Okay, let me share my screen. Okay. Hello, everybody. I'm Leah. I'm a new Einstein Fellow at UMD College Park. And yeah, sad to miss this. It sounds like a lot of fun, but I'm going to tell you a little bit about explaining the millimeter axis in radio quiet AGN. So first of all, I guess here we go. Yeah. So the X-ray corona is this kind of notorious. Yes, what's up?
I'm sorry. The thumbnail views of you and us are right in the middle of your screen, blocking your slides. The small videos on Zoom.
Small videos are okay.
That's not us, is it? Oh, it is us. Oh no. Never mind.
Okay.
Please continue. Sorry.
All right. Does it look okay now? All right.
Leave her face there. It's just us.
Yes, just put my face in the middle of the screen. Okay. Yeah, so the X-ray corona is this really interesting sort of a thing in both X-ray binaries and active galactic nuclei, so both stellar mass and supermassive black holes where we see this. I put a spectrum of an AGN here just so you could get a sense for what I'm talking about. The thin accretion disk that's around a black hole is here in dark blue, and then the corona is this light blue sort of a thing that's thought to exist. Now, exactly what the corona is a very, very active field of research right now. So I put kind of a schematic diagram over here, but what we think the corona is this population of very hot electrons, so somewhere around 10 to the 9 Kelvin. That means it's collisionless, so the electrons do not undergo Coulomb collisions in there, which means that non-thermal particle acceleration is not only possible, but we can also then see that non-thermal population of electrons. Now, the really cool thing about the X-ray corona is that it's thought to come from within the innermost 10 gravitational radii of a black hole, where 6 the event horizon of a non-spinning black hole is 2 gravitational radii, for example. And so the corona has
Sorry, Leah, we lost your audio. Can you hear us? Yeah.
Yeah.
Oh, sorry. What I'm going to do here is you can still hear me, right?
Yes, now we
Yeah,
can.
okay, great. What I'm going to do here is build from saying, okay, let's assume that the corona is magnetically powered and then kind of follow out the consequences of that. So to that end, we take it as a hot 10 to the 9 Kelvin object with very compact within 10 gravitational radii. Now let's just say that the X-ray luminosity comes from dissipated magnetic energy. That's what it means to be magnetically powered. So if you do that, then the X-ray luminosity has to convert some fraction of the magnetic energy density in this, and that actually gives you a lower limit on the magnetic field in the corona that depends on things like the X-ray luminosity, black hole mass, and radius of the corona. Now you might notice this is actually kind of a large magnetic field for all things considered. So with that large magnetic field and this non-thermal population of electrons due to reconnection or turbulence, you would expect to have some non-thermal synchrotron emission. So the question is, where is the synchrotron emission that you might expect? So if you calculate where that synchrotron emission would be, you might think it'd be in the radio or the millimeter wavelengths. So if we're going to probe this astrophysically, we have to look at radio quiet AGN, which means that there's no jet, because otherwise the jet will just swamp everything in the radio and millimeter. So again, let's say it's compact, close to 10 gravitational radii, and just take like a Rybackian-Lightman radiative transfer sort of a thing. And you'll notice that there's optically thin emission at high frequencies. This is kind of the classic synchrotron power law of P is the underlying electron distribution function slope, and the radiation is just related to that power law index of the electron distribution. But that only goes down to a certain turnover frequency, and that turnover frequency is where the electrons start absorbing the synchrotron emission that they're radiating again. So this is called the synchrotron self-absorption regime, and it happens at this turnover frequency. And below that turnover frequency, the radiation drops off extremely quickly. So if you calculate that turnover frequency for this typical magnetic field that I plugged in, it's actually very, very high. So 10 to the 13 hertz, which is above millimeter range, for example. So if that turnover frequency is at that wavelength range, this nu to the 5/2 is going to cut out all of your synchrotron emission from these coronal electrons. So there would be no hope at all of seeing the coronal emission. However, there's this idea I'm going to talk about here is that what if it's not a single compact, one zone model for the corona? What if instead there's this outflow? Now, this outflow is motivated by general relativistic magnetohydrodynamic simulations of black hole accretion disks. You can get these winds that are mildly relativistic coming off of the very inner parts of an accretion disk. Now, the thing here is that you actually have a magnetic field gradient. So you have higher frequencies that are coming from smaller radii. And then as you go up, you have a lower magnetic field. And so you actually get optically thin synchrotron emission from at lower frequencies. So the idea here is that you take each stacking part of the outflow, gives you a different classic synchrotron absorption spectrum, and then adding all of those up together will kind of give you this flatter slope so that instead of being totally cut off, you actually have a chance of observing it. For those familiar with relativistic jets, this is similar to the Blanford-Koenigsegg model. All right, so now I get to talk about observations here. So this is actually what seems to be potentially a new characteristic of the AGN spectrum. So this is called the millimeter excess. And if you look at a radio quiet AGN in the millimeter, and you try to accounting for all of the millimeter emission from, for example, dust, then there's this excess. And this excess has certain characteristics that are outlined in this slide. So for example, it has a very flat spectral slope, here measured to be right around 0. It's also, if you relate the luminosity in the millimeter to the X-rays, then there's this very nice linear relationship between those two luminosities that has a given, value of 10 to the minus 5. Then you can also plot it as a function of black hole mass rate, or black hole mass, and find that it's roughly mass independent. There's also things like variability and time lags that you can talk about. So now let's see what our model could predict for the spectral slope. Because remember, we were summing up the contributions from different wind heights. So we're getting a flatter spectrum than that nu to the 5/2 synchrotron self-absorption limit. So if you analytically calculate the dependence of the slope, you find that it has this, just call it alpha. You don't really need to know what it depends on, except it depends on the density profile, the magnetic field profile, and also crucially on the population of non-thermal particles in here. So this is just an example showing this blue line is if you had just a compact sphere, just that one zone sort of a model again, you get, that really steep cutoff here. This dotted line is 100 gigahertz where we observe the millimeter excess. If instead of having a constant magnetic field, you put in a falling off magnetic field, then the profile becomes that stacking up and it becomes much more shallow. So theoretically predicting that slope from that model that I was talking about, you can get this ratio for how the millimeter luminosity compared to the X-ray luminosity should trend with, for example, magnetic fields. The interesting thing here is that, this probably magnetic field is not constant with black hole mass, although feel free to talk to me or ask me something about that, or I'd love to hear from people who think otherwise. But the thing is that for particle acceleration, that's, getting that population of electrons to radiate in the first place, that efficiency of particle acceleration does not depend on the magnetic field, but rather on this parameter called magnetization. So it also incorporates density. And so that number is probably more constant with mass. And basically you need this number to be somewhere greater than 1. And it's expected to have a value of between 10 and 100. So you can also get a mass dependence, and that should predict what this coefficient should be. It constrains this model because this coefficient should be close to 0 based on those observations. And so we can constrain what the magnetic field profiles and density profiles and that non-thermal electron profile is. So this is a case study, like actually plotting some spectra for different black hole masses. You can see we have that nice stacking up, goes and gives a pretty flat spectrum, especially at that 100 gigahertz where this feature is measured. And as a function of black hole mass, you can see I've plotted just a few different parameters here. So like that magnetization in the corona, then the electron, how deep that electron distribution is, and then where the outflow actually starts. And you can see it's like promisingly close to that observational plot that I showed earlier. Yeah, and so this has implications for variability and simultaneous X-ray to millimeter, which has been something that people are trying to constrain right now. You can calculate, for example, variability based on just a synchrotron time there, which is constrained by like it should be somewhere around 5,000 seconds, for example. The other interesting thing is that if you're trying to do a correlation between X-ray and millimeter, which is a common way to kind of figure out where it's coming from, this model would predict that it's not the same electrons that are radiating. And so because you're contributing from multiple heights. And so that correlation might be a tricky thing to do. But the very interesting thing here is that, you have to reaccelerate electrons continually along the outflow in order to see them radiate. So that has implications for kind of figuring out what the dissipation mechanisms in the corona is. So with that, I have my conclusion slide up here. The thing that I think is super interesting is that this millimeter emission could actually be probing dissipation in the corona. And one thing that I look forward to doing in the future is kind of probing that continual reacceleration mechanism and trying to look at, magnetic turbulence versus reconnection and trying to put that all into this bigger picture. So if you assume the corona is magnetically dominated and it's in a compact region, you're going to be synchrotron self-absorbed, which means you have to have an extended region, which means you have to have this inhomogeneous coronal outflow. And this model so far has been pretty good at reproducing observations, but I'm looking forward to doing some more on that front. And with that, I'm ready for questions.
Yeah, how does this rescale and how is it applicable to the X-ray binary case?
How does the what scale?
How does the model rescale and the observations and what you expect in the X-ray binary case?
Yeah, so X-ray binaries have a different, it's called it has a different, like the synchrotron self-absorption is not as important for X-ray binaries. And so it has a different, it doesn't apply as well to the X-ray binary case.
Okay, we have no time for other questions, unfortunately, but if you have more, then ask on Slack. Our next speaker is Ricardo Arconia, who will be telling us about repeating X-ray plans as probes of the dynamics of galactic nuclei. Ricardo, do you want to share your screen?
Yes. Can you hear me well in the meantime?
Yeah. Cool.
Awesome. Are you able to see the slides?
Yeah, we're good.
Awesome. Thank you so much. Yeah, thanks for giving me the chance to present remotely. I'm Ricardo for the ones that don't know me. It's a shame that I'm not there in person. I can't wait for next year. And I try to fight the FOMO by adding myself in Photoshop to the group picture, hoping that it's gonna be the faithful case for next year. And I promise that this is the only forging that I'm gonna have in this talk. I'm gonna present this type of transients that I'm working on. They're called X-ray quasi-periodic eruptions, and they're a relatively niche topic. So I'm gonna give you an overview, and I'm gonna leave you with a few take-home messages, maybe poking you for collaboration. In essence, everything started a few years ago. It's a very recent science field. At the end of 2018, this galaxy, relatively unimportant, was being monitored in X-rays. And colleagues from ESA in Spain, they started observing these crazy soft X-ray flares that would repeat every 3 hours. And now, as you've seen from the previous talk, typical X-ray emission is pretty much like a non-thermal hard X-ray component, which varies stochastically. So this is something completely different. It was never seen before. It required a new name, and this name was chosen to be QPEs, quasi-periodic eruptions. And so essentially, 5 years roughly from then, now we are at a point in which we know of 10 galaxies that are doing these crazy QPEs, and seven of which are actually in published papers. Some of them are in preparation. So we're starting to building numbers to do some preliminary sample analysis, if you want. But they all have in common that these signals are coming from massive black holes in low mass galaxies. The typical masses are on the order of 10 to the 10 solar masses, so lower than the Milky Way for the galaxy. And the black hole mass estimates point towards 10 to the 5 to 10 to the 7 solar masses. So these are small black holes in small galaxies. And compiling all the timescales across all these handful of sources, in a plot that shows the duration on the y-axis versus the separation in time between the bursts on the x-axis, you see that they might form a correlation. I mean, maybe the numbers are too low for now, but most importantly, that the timescales are fairly short. You know, the bursts last from half an hour to maybe over a day, and they repeat from a couple of hours to a few days. So these timescales are very short, you know, for nuclear galaxies, if you're familiar with this science. But essentially, the ingredients we have at this point to just try to find a possible model for this origin is that we have this massive black hole in this galaxy, and the fact that these signals come from the black hole comes from the localization, but also the high luminosity, because we're looking at 10 to the 42 to 10 to the 44 erg per second at the peak. And then we know from UV and soft X-ray observations from when the source is not flaring that there is an accretion disk around this black hole, and it's radiatively efficient. So these are compact, luminous accretion flows around small black holes in small galaxies, at the center of small galaxies. And then on top of this, we see these X-ray flares. And what we know to date is that they're only observed in X-rays. We don't have any counterpart to the flares in any other wavebands. So their SED is probably very narrow. And particularly, I stress again that these are Howard's timescales. And if you're familiar with accretion around, well, any sort of black hole, you'll immediately notice that these are way too short for being thermal or viscous timescales around black holes. They are this massive, and that's why people pretty quickly started thinking about something more on the dynamical point of view. So this could be actually the dynamical timescales around these black holes. And so over the years, people started being tempted about modeling these sources with a high mass ratio orbital system with a primary massive black hole and an orbiter which is much smaller in mass, roughly in stellar mass object, which is in a quasi-circular orbit, and it pierces through the accretion flow, and that's what it produces the X-ray flares according to some models. Now, obviously, we're not only drawing cartoons on PowerPoints. There's been a lot of work in the last year, pretty much, from the theoretical point of view, to try and explain this phenomena. And I'm really happy to see that, you know, this summer already we had the first dedicated simulations to QPE, so it's picking up. A lot of theorists are getting engaged by the problem. And so what's left for observers is now trying to actually test this model. And other models have been more or less ruled out so far, mostly because they had higher predictive power. And so we're trying to do the same with this one now. And it's particularly intriguing because these systems, these high mass ratio binaries, are actually detectable through gravitational waves emission. This orbit will lose energy through gravitational wave emission. And whether, depending on the type of orbiter, whether it's a black hole or a star, it will matter on whether these systems are detectable by LISA relatively soon, or by some future generation microhertz detector. This is TBD, of course. But obviously, this is such an intriguing case that everybody's getting excited. We all want this to be the right model. But as an observer, one of the takeaways is that we're working on this, but we're still far from testing or rolling out this model, although it does make sense. And I'll show you qualitatively, if you want, the ingredients of this test and the difficulties. For instance, if we have such a system, we expect many effects to be at play. For instance, I'll guide you through this slide from left to right. For instance, we expect the orbiter to precess, so the Emery apsidal precession within the orbital plane. We would expect the orbital plane to precess itself if the black hole is spinning, the primary black hole is spinning. In most cases, we would expect a compact accretion flow to also precess, especially in the case in which this is a very newborn accretion flow, which comes from an arbitrary angle compared to the spin of the black hole. And then we know that this orbit should lose energy. And there are a couple of mechanisms. One is gravitational waves, very slow, barely detectable, fraction of a second per year. And if the orbiter is a star, we should be able to test with an effect of tens or hundreds of seconds per year, the effect of the energy lost due to the collisions themselves. Now, all these effects are acting on different timescales, and some of them, particularly the disk nodal precession, are very uncertain. They're pretty much a wild card. So this is very hard, and particularly so because the typical observation probes a timescale of a day, and the typical gaps between observation is of about a few months to a year. So with the single observation, you're barely sensitive to some of these effects. And if you combine multiple observations, the gap between the data is so long that some of these effects have played a role in between these two observations, and it's really hard or impossible to disentangle them. And this was the case because, the first follow-up observation we took in the last years were not aimed to test this model in particular. So we found ourselves with the task of trying to test these models with observations that were made to test this model. But we've tried nonetheless. For instance, what we can do is still take epoch by epoch the data we have and try to see whether the model makes sense qualitatively, whether the consistency checks are all in place. And one can also fill the gaps between observations using models and predicting forward the possible evolution of the system, but in a model-dependent way. This has been done in a few papers recently, one on my own this summer, but I want to highlight here a paper led by graduate student Johin Chakrabarty from MIT, who's done an amazing job in trying to analyze the data of one particular source. And we think we have seen what could be the effect of the disk nodal precession in the data. This is not a confirmation of the model. This is an assumption of the model. And we checked whether within the data we find effects that could reproduce the observations. The way forward is naturally to try and roll this model out or test it. And so last year we started asking data in a way that would be, would allow us to test this model more conclusively. And this is work in preparation. This campaign has started about 2 months ago. So I'll probably present this next year at the next symposium. Now, with the last couple of minutes, I think, I'm not sure exactly when I started, but I think I have another minute. Feel free to tell me otherwise. I'll tell you that if this is the correct model, we can actually do a lot of useful things for the future of multi-messenger astronomy, because from observations, I was able to basically infer the intrinsic rates of these events. Now you see a luminosity function, so number density of sources as a function of luminosity. The leftmost y-axis is unit of volume, and the rightmost in unit of galaxies. And integrating this number gives you an abundance rate, which is a number per volume or a number per galaxy. And so from data, purely from data, we can tell that one galaxy every 10 to the 4 in this stellar mass range is emitting QPs at any time, at least above this detectable luminosity. And this is one observable. It comes from data themselves. And then if we want to try for now to assume that QPs are memories, we can see what the consequences will be for LISA. In particular, we see on the y-axis here the number of events per year detectable by LISA as a function of a quantity that is only relevant for QPs. It's the unknown lifetime, how long they last. We know that it's a list of years, but we don't know exactly how long. So you see in black the predictions for LISA. They span 3 orders of magnitude from theoretical arguments. It's a very uncertain quantity. So that's why having something from data would be very, very useful. Now, if the QP rate that I get from data is exactly the rate of black hole memories, if QPs are exactly black hole memories, I get this lower limit in green here, because effectively not all memories will be observable as QPs, but there will be at least as many memories as there are QPs. So it's a lower limit. And it would be particularly optimistic, there would be many, many, many memories, way more than the LISA people thought. If instead QPs are stellar memory, if they're stars, there has to be a conversion factor of the stellar to black hole memories, and therefore the lower limit is the yellow one. This is an 1 sigma uncertainty range. As you can see, it's very uncertain. And in this case, perhaps the constraint would be less stringent, but still particularly useful. And this is obviously early days. I hope that actually next year the symposium will present what could be the smoking gun, that this is the correct model, or that we will have proved that we ruled this out. And in the meantime, I'll thank you for your attention. I'm happy to take questions.
Yes, so I had a question, are there any new developments in detections of QPOs that go alongside the QPs?
So if you weren't able to hear that, the question was whether there are new detections of QPOs going along with the QPEs.
That's a very good question. You've been reading the literature. In some of the sources, there has been, in actually, very clearly in one source, there's been evidence of a QPO with the same recurrence time as the QP, but with a basically quasi-sinusoidal amplitude. So a phenomenon that has been seen in other accreting systems, but it's not immediate as to how you would tie it to these events, but it could be a sort of response of within the disk due to the collisions, and maybe we just see it in the system which has the right combination between inclination and brightness of the disk, or maybe this is completely unrelated. We don't know yet. Good question.
Any other questions? Tom?
Maybe a pretty naive question, but it seems, since you didn't mention it, that there's no thought that this could be like a processing axis of, like a X-ray jet that points towards us every 9 hours or something. Is that because you would definitely expect radio emission to go along with it?
Yeah, no, it's not a naive question. It's actually a good question. So there are maybe few elements that would point towards some other mechanism. So the spectrum is very thermal in the soft X-rays, and there is no radio counterpart at all. And we have simultaneous VLA data to some of these flares, and there's nothing. So the SED would be something that we've never seen before. And it's not any jet emission that we can scale from any other accreting source. And it would imply that there's quite like a conspiracy of a cutoff that just gives you like a thermal decay, like an exponential decay in the soft X-rays. And another factor could be that we see when the sources are not flaring, a very stable quiescence emission from the accretion disk. So we would need to basically have a very complicated combination in which the jet processes, but not the inner accretion disk. But maybe this is my naive reply from an observer's point of view. You can tell me if this doesn't make sense.
Okay, we must move on. Let's thank Ricardo again.
Thank you so much, and I'll see you soon or next year.
Okay. Next speaker is William Rosich, who is going to talk to us about revealing the physics of accretion disks with Hercules and so on.
Hello, can you hear me? Okay, thank you for the introduction. So my research focuses on physics of accretion disk winds in various accreting systems. And today I'll be talking to you about one particular system which I've been working on and studying for the past few years, and which is really fascinating because it allows us to reveal the physics of disk winds in ways that we really cannot access anywhere else. So disk winds are wide-angle outflows of material launched from accretion disks of various objects. They come in many different flavors and types and have a huge range of properties. And they've been observationally confirmed in many different systems. That includes active galactic nuclei, tidal disruption events, accreting supermassive black holes, then X-ray binaries that this talk is going to be about, so accreting stellar mass black holes and neutron stars, and even accreting white dwarfs. There are a number of possible theoretical launching mechanisms for these outflows that include radiation pressure, either isotropically or on specific UV lines, or these outflows can be launched by magnetic fields or thermally. These phenomena are of interest because they can theoretically carry away a large fraction of the originally inflowing mass. So they can strongly modify these accretion flows of different accreting systems. They can modify the amount of matter that black holes accrete. And secondly, if these winds are launched from the inner accretion flow, they will have huge velocities of about 0.1 speed of the light. Therefore, they carry huge kinetic powers. And if this power is sufficiently deposited in the neighborhood of the accreting system, it will strongly affect it. So for example, high velocity outflows from accreting supermassive black holes are strong candidates for driving AGN feedback in galaxies across our universe. And then thirdly, through these outflows, we can measure elemental abundances of this material, and therefore we can learn about the composition of the material that's being accreted and ejected. So unfortunately, despite studying these phenomena for the past decades, we still do not really know, at least in most systems, what is the exact mechanism that is powering these phenomena, which could be different across different systems. And also, we still struggle to constrain these wind energetics and mass outflow rates, which would inform this impact of, or which would tell us the impact of this on the surroundings by these phenomena. So as the outflow is lifted from the disk, it is illuminated by the X-ray source of this accreting system, and therefore it is ionized. And so we can study its properties by X-ray spectroscopy, which contains transitions from a large range of ionization states. If this outflow passes across our line of sight towards the X-ray source, it will produce an absorption line spectrum. And these absorption line spectra are particularly useful because they're relatively simple to interpret with X-rays. However, they have one big disadvantage, that is that they only sampled at one point where the outflow is crossing our line of sight towards the X-ray source, which is often very compact. So we are completely blind to this big 3D structure of this outflow, and therefore it's difficult to infer proper 3D properties like the total mass outflow rate, total energetics of the outflow. Instead, the material out of our line of sight towards the X-ray source will re-emit some of the radiation towards us, producing an emission line spectrum, which then encodes this full 3D structure, but it's also much harder to interpret because we have to interpret this whole 3D structure. Additionally, at least specifically in X-ray binaries, these emission lines are very weak. Here on the bottom right, I'm showing an example of very high quality X-ray spectrum of an X-ray binary, where you can see that the absorption lines are very strong, very easy to interpret, but the emission lines, even if they're there, they're much weaker, much harder to model, and their modeling can be degenerate because there are also other sources of emission lines that are not just the winds. A second big issue is that while we can measure the column density of the outflow, so basically the amount of mass across our line of sight towards the X-ray source and the ionization state of the outflow, we almost never measure the outflow number density. But number density is a crucial parameter to place the outflow, to determine its location, and to determine the energetics. Now in this talk, I'll be presenting Hercules X1, a really interesting X-ray binary, and I'll argue that with this source, we can actually solve both of these issues. And I'll explain why. Hercules X1 is a very famous X-ray binary, which was discovered in early 1970s. It was one of the first X-ray sources actually found, and it's very famous for this 35-day cycle of high and low states. This repeats for basically the past 50 years with some breaks, but it's very consistent overall, and it has been studied extensively. And the interpretation is that this source is an X-ray binary, so it's a neutron star accreting from a regular star, and it has a warp disk that's placed almost edge on and is processing with a period of 35 days. So there are times when we can directly see the accretion flow, which produces most of the X-rays, but then there are times when the warp disk processes such that it obscures our line of sight towards the X-ray source and we see a low state. Here is a very nice simulation of what this disk could look like from Hickox et al. So most of the time, some part of the disk is obscuring our line of sight towards the inner accretion flow, and we see a low state. But there are some periods of time when we can directly see the neutron star, and then we see a high state. So to conclude, this is a source where our line of sight towards the X-ray source is really changing. And this source has been studied really extensively for the past 50 years, but not from the point of view of accretion disk winds, which we only discovered in 2020 in this system. And that's when I had an idea to leverage this warp disk precession, because this means our line of sight across the wind streamline, is probing the wind at different heights above the disk at different places of this disk precession cycle. So by studying how the wind is changing with precession phase, we're studying how it is changing with height above the disk. So this is what we proposed back in 2019 to observe, and we executed a large observational campaign with XMM, Newton, and Chandra to study how this wind is changing. And here are 3 observations from this campaign. Luckily, this is a very bright source, so we don't have just 5 X-ray photons. But you can already see that the absorption lines which come from the wind are changing very rapidly as the disk precession is increasing, going upwards. Basically, at low precession phases, when we are studying the wind close to the disk, the lines are strong, and then they weaken as we're probing the wind at greater heights above the disk. So doing this more systematically, we analyzed all of the observations of this source that we had with photoionization models, and we measured the column density of the outflow shown in the top panel and the ionization state of the outflow. So at low precession phases, again, when we're sampling the wind very close to the disk, the column density is very high, the wind is strong. But as we progressively go higher and higher in the flow, the wind is getting weaker and weaker by 3 orders of magnitude in column density. So the wind is weakening with height above the disk, which makes sense because it's expanding into space. This is also in agreement with statistical studies of X-ray binaries, which show that strong winds are only detected in high inclination sources, so when we are probing the wind very close to the disk. Now, from these parameters that we measured, we can start inferring what is roughly the distance of the outflow from the ionizing source. But what is really cool here is we also know where the sightline should intersect this outflow, because we can model the warp disk precession. Therefore, we can place this outflow in 2D and create for the first time a 2D map of an accretion disk wind. So what we observe here is what looks like a streamline that originates somewhere where we would expect a thermal disk wind to be launched. Then it is launched from the disk at an angle of about 12 degrees away from the disk. And as it expands into space, both the ionization and the column density is dropping as it is expanding into space. So I also mentioned that there is a second issue with these X-ray spectroscopy measurements, and that is that we almost never measure the number density of the outflow. However, Hercules can actually probe this parameter space also because it is powered by an X-ray pulsar. So this source is powered by a highly magnetized neutron star, the magnetic field of which is so strong it disrupts the inner accretion flow and then channels the accreting matter onto its magnetic poles, as shown in this simulation. And this process produces very anisotropic emission. And at the same time, the neutron star rotates every 1.2 seconds. So this outflow is being periodically illuminated by X-ray pulsations every 1.2 seconds. And since this radiation is time variable, the outflow changes its ionization state to respond to this variation and regain ionization equilibrium. And what's very powerful here is that the speed of this response is inversely proportional to the number density of the outflow. So we can simulate how this ionization response looks like, and we use the TIFO, time-dependent photoionization code, to do this. So in the top plot, here, this is just the X-ray pulsation of the source. And in the lower 2 panels, I'm showing the column density in 2 of the strongest iron absorption lines from the wind. Basically, for low densities of the outflow, so for 10 to 10 or lower per centimeter cubed, the outflow is so tenuous, the density is so low that it doesn't have time to respond to these very fast 1-second pulsations. But if we increase the density to about 10 to 11, we see a response that is there, but is clearly delayed with respect to the pulsations. For very high densities, like 10 to 12 or higher per centimeter cube, we see that the outflow immediately responds to this pulsation. Basically, when the X-ray flux increases, some of the iron atoms get fully ionized, so the column density goes down. When the X-ray luminosity goes down, some of them get recombined, and again and again. And what's very cool is that we can actually see this in real data. We performed a pulse phase resolved analysis of the best quality XMM dataset that we have on Hercules X1. And instead of focusing on individual lines, we just looked at all lines at the same time and measured the ionization state, and we can clearly see that that the ionization goes up as the X-ray flux goes up, which already constrains the wind number density to be at least 10 to 12 per centimeter cube. However, this is really pushing the current data that we have on this source, and we really need a better telescope to study this source with, and that telescope exists right now, and it's called GRISM. It was launched roughly 1 year ago, and it offers a much better spectral resolution than all of the previous telescopes that we had, which you can see on the simulation on the bottom right. And so GRISM will be able to do precision mapping of this wind and its ionization response to X-ray pulsations. And actually, this is already the present because we proposed to observe this source with GRISM and were approved a large campaign, which was carried out just last week. So stay tuned for more very exciting results on this source. Here are my conclusions, and I'll take any questions. Thank you.
So what warps the accretion disk, and how is there a way to measure the degree of warping with these data?
So the exact process of the warp is unknown, but one of the possibilities is actually the wind that is torquing it. The other possibility, I think, is thermal torquing, but I think it's not clear which of these two processes it is. But we can probe the angles of the torquing, like the inner angle or the outer angle, and the twist between the inner and outer rings by studying when the source turns on and turns off. So this is possible to determine, and that's what we use to get the map of the disk wind.
The talk after next is all about warped accretion disks.
Okay, so we are still behind schedule, so I think we could truncate questions here. Our next talk is from Sarah Islam, who will show us a photo of Sagittarius A star. Sarah,
Thank you. Hopefully the screen share is okay and you can hear me.
Yeah.
All right. So thank you very much. So my name is Sarah. I'm in my last month as an Einstein Fellow at the Smithsonian Astrophysical Observatory. So before I get started with my talk, I'd like to take the opportunity to thank the leads and the program for the amazing opportunity that to be a fellow for the last 3 years. I had a blast and I really enjoyed the freedom of being able to do my own research for this time. And I'm very sad that I can't be there with you all at Caltech for this last presentation. So what I'll be talking about today is the first polarized image of Sagittarius A star. I've worked the last 2 years on this project as the project lead as part of the Event Horizon Telescope collaboration, but it was under embargo for so long that I wasn't able to talk to you about it until the papers were published this year in March. So I'm very excited to finally be able to share this with you. Yeah, so let's get started. So for people who are not too familiar with the Event Horizon Telescope collaboration, we made these 2 pictures, the first images of black holes. And of course, we'll look at lots of other cool jet sources, but these 2 black holes are really the only ones we're reaching on Event Horizon scales. The M87 star black hole resides in the M87 Large Elliptical Galaxy. It's 55 million light years away from us, and this black hole is 6.5 billion solar masses. It's one of the most massive in our universe. And M87 is particularly special because it's one of those big lighthouses in our universe that generates a jet coming from the center of this galaxy, powered by the black hole, and pierces the entire galaxy. In fact, it was the first astrophysical jet ever imaged back in 1918 in the optical. So M87 is pretty special in that sense, whereas Sagittarius A star is interesting because it's the total opposite. It's very, very common. It resides at the center of a Milky Way, which is a very basic spiral galaxy, pretty ubiquitous in our universe. It doesn't seem to have jet emission coming out of it. It's very underfed, and it's 27,000 light years away from us, but it's 4 million solar masses, much, much smaller than M87. I really like this diagram that Leah, who's also an Einstein Fellow, you heard from her earlier this week. So she adapted this from a comic from XKCD that showed the scale of M87, but she adapted it for Sag star. And it shows the difference in scale between the two black holes, where M87 is so large that the shadow could completely encompass our solar system up until where Voyager 1 currently is. Sagittarius A star fits very snugly inside the orbit of Mercury. So M87's large size means that light needs to take a lot more time to travel around the black hole. In fact, it takes several days to make an orbit. So when we're looking at it with the EHT for a period of 8 hours, and we're stacking data in time and spatial frequency with this technique called very long baseline interferometry, or VLBI, we're stacking data on times when the source is basically static on the sky. So we're able to make an image much easier. For Sag star, on the other hand, it takes like mere minutes to orbit around the black hole, which means as we're looking at it for a single observing night stacking data, the source is changing on very, very fast timescales. So we're actively dealing with motion blur and variability. This made Sagittarius A star a lot more challenging to deal with, especially just to make the total intensity image. So we were very nervous starting out with a polarization project about whether we'd see anything at all in polarization, whether we'd even be able to make an image of it. But fortunately, we were able to achieve that challenge, and it turns out Sagittarius A star is a lot more interesting in polarization than we had expected. So starting with the first observations of Sag A star in polarization with VLBI, in fact, there are only observations with very early EHT that were able to resolve Sag A star on small scales. And these were done in 2013, and what we learned is that we had pretty strong polarizations on long baselines. This is far telescope spacings. And what we were seeing in the data here is that we're seeing asymmetric polarization on different spatial scales, which implies spatial changes in the polarization direction in the image. But of course, these were very few data and not sufficient to make an image. So polarization observations of Sag A star have been done for the last decades, and both with interferometer, single dish, and with VLBI. And what we've learned about it were actually pretty significant breakthroughs on our understanding of Sag A star. They were pretty decisive in establishing Sag A star as a very underfed black hole. They were the best window into variability of Sag A star, and we got multiple lines of evidence for persistent and partially ordered magnetic fields near the black hole. Unlike M87, there are really almost no previous polarimetric measurements of Sag A star using VLBI and 0 images in polarization. So moving on to what our campaign looked like for 2017, these were the 2 observing days that were where the source was quiescent enough for us to make total intensity images. And this is what the data looked like in polarization. If you remember the plot I just showed you from the proto-EHT, which has very abysmal kind of a handful of detections, we are seeing really booming data across different pairs of telescopes here in our UV plane. We're sampling different spatial frequencies, and they're seeing quite different polarization fraction and polarization direction, which shows that the source structure is actually complex. So going into image reconstruction as our typical EHT fashion, we really strive to use multiple methods in order to have diversity in the way we analyze the data, and also redundancy across methods. So for this particular result, I spearheaded the use of 4 independent methods, one of which was using a ring model fitting, and the other 3 were reconstructing pixel-based images. So without going into too much detail about these methods, all of these methods had different starting bases, assumptions about the image. They used different data products. Some reconstructed total intensity, linear, and circular polarization all separately as separate images. and some reconstructed a full Stokes full Stokes image of the source. They use different variability mitigation schemes. Two methods used a variability budget and then reconstructed a single image from that. And then two methods actually created multiple frames of images of the data in small snapshots and then reconstructed an average image from that data. Different image products were reconstructed. Some used large surveys of parameter space for their software, and some used posterior exploration methods as part of their software. And because of these big differences, we're pretty confident that wherein they agree in what we see, these are really signals on the sky and not artifacts of the analysis. So understanding our images, just to give some background of how the EHT does this. So we start with data calibration. We go into a blind imaging stage with independent teams, and we go through a feedback on data quality using blind imaging metrics. Then we unblind the data and the images, and when we go into a systematic pipeline building step for independent software, in which we train our softwares and evaluate different parameter choices based on synthetic models where we know the ground truth. And we can evaluate the software performance. Then we validate our images against how well it fits the data, how consistent we are with the calibrator analysis, so sources that we co-observe, and how robust the structure is to different choices in the analysis. So these were the final results from the teams for the 2 days of quiescent Sagittae. The top two methods are the posterior exploration methods, and they were the ones that achieved the best results on our synthetic data tests. So they were the primary result methods for theory analysis. And then the bottom ones were used as additional imaging methods for validation. So what we're seeing here is quite different total intensity patterns for linear polarization. These are these kind of dotted contours. This is what we expected, because in total intensity, we also weren't sure about the overall intensity distribution on the ring because of the variability in the source. But where they agree is that really they're all seeing most of the ring have polarization, and they're seeing these EVPA patterns, these ticks that we're seeing on the image, twist in the same direction. And this twist of the EVPA pattern is really, really robust across all our parameter checks. So we created a final method average image that looks like this, where most of the ring has linear polarization fraction, and we're getting this polarization twist pattern that's very coherent and stable. We also reconstructed circular polarization images. Here, all methods actually reconstruct negative circular polarization on the west side of the ring. And both the best methods also find an east-west dipole structure. But overall, all methods kind of prefer very simple polarization structures compared to linear polarization. But the circular polarization structure here is more uncertain because we're seeing wider differences even within each software of what the structure should look like. So we're not certain compared to the linear polarization structure. So circular polarization is not used as strongly to determine the theory results. So this is what Sagittae looks like in sort of the quintessential VLBI look of it, and this beautiful line integration plotting scheme. So what we know about Sagittae is that it has a very low accretion rate. This means it has a puffy, hot accretion flow. The synchrotron radiation we observe is intrinsically polarized, and it traces the magnetic fields. The non-polarized image already preferred models that were non-zero spin and relatively face-on towards us and strongly magnetized. What's new now is that we have this large polarization fraction and this rotational symmetry from the EVPA pattern. So we go check our theory models against our large library based on this evolution of magnetized torus and in Kerr spacetime, and then solving for these trajectories of light and polarized radiative transfer. So the structure of the magnetic fields tell us about what we're seeing in the image. So magnetic fields that are that have field lines that are circular around the black hole. When we're emitting synchrotron radiation, they arrive at the image in sort of a polarization configuration that looks like spokes on a wheel. that are radially outward facing. And then if we have a different magnetic field configuration, and we're seeing more spiral-like structure for the magnetic field lines, then what we're seeing in polarization structure is also kind of like a spiral structure. And this is what we see for Sagittarius A star. We see this spiral-like structure. We also have to deal with additional effects from magnetized plasma called Faraday effects. And we undo this effect by measuring rotation measure caused by Faraday rotation. For a Sagittarius star, which has a pretty high rotation measure, we observe one that's corresponding to a rotation about 46 degrees. However, we're not sure if all that rotation is coming from an external screen or if it's internal to the system. So we look at the two different scenarios. We're looking as observed, which implies a counterclockwise inflow of the gas. Or if we derotate fully, we get a clockwise inflow. So if we look at the as observed one, so no derotation, we're mostly seeing moderate inclination models that pass, counterclockwise flow, mostly magnetized arrested disk. This is inconsistent with the total intensity cuts that we had previously. If we apply the full rotation, we now get a clockwise rotation, and this is consistent with total intensity constraints. And what's interesting is that our best bet model shows that we're getting a magnetically arrested disk just like M87. So the main question is this really universal to supermassive black holes? And most of the emission is actually coming from the jet due to spin extraction efficiency, which means that Sagittarius star may have a jet if this model is true. So I'll just close off by showing the images of these two black holes in polarization. M87 is showing the same kind of spiral structure, which shows that it's also strongly magnetized with ordered magnetic fields. And we know M87 has a jet. So this particular configuration is able to launch the jet in M87. Sagittarius star shows a bigger mystery because it really looks like it is able to launch a jet. So I'm happy to take questions now. Thank you.
We have time for one question. Karen?
Sorry, I'll just screen. Super cool talk. I think about polarization kind of in my day-to-day, and I was particularly interested in your figure about circular polarization. Can you think of this, or do you have a hypothesis as to where the discrepancy between different kind of packages modeling the circular polarization might come from?
Yeah, so in case of the circular polarization, we're seeing because the variability in the data is quite significant, and the different methods deal with the solving of gains between right polarization and left polarization feeds differently. They end up with different constraints in the circular polarization structure. The variability is really what's causing most of the spread in data. I think our instrument is just not too sensitive for circular polarization at the moment. What we're seeing is really a circular polarization fraction of the degree of about -1%. So it's very, very low. For M87, we were unable to get a circular polarization image at all because the circular polarization signal was too weak and the data were too noisy.
Okay, we have to move on. Our last speaker is, I think this guy is going to talk to us about quark accretion disk.
Yes. Oh, yes. Here, everyone hears me? This one?
Yeah,
Yes, it's on.
just hold it close.
Good. Yes. Yeah, so thanks for coming to my talk. I'm now in second year Hubble Einstein Fellow. Soon I will be transitioning to a faculty position at Georgia Tech. In this talk, I'm going to tell you something about what we can learn from numerical simulations about accretion disks that accrete close to the Eddington limit. And yeah, many of those are potentially warped. I study these accretion disks in a wide variety of contexts, of course, XRBs, but also AGN. We also have some work about core collapse supernovae now. And last but not least, mergers between neutron stars or neutron stars and black holes. Well, these two are very exciting. I'm not going to talk about them in this talk. Focus on accretion disks and outflows in the context of black hole X-ray binaries and AGN. These accretion disks don't come in a single size or shape, as we know from observations from both XRBs and AGN. Accretion disks are found in various different states. On the top end, with respect to the Eddington limit, so let's say above 1% of the Eddington limit, you have the two luminous states, which are the high soft and the hard intermediate state. I call them luminous accretion disks. And then you have at accretion rates below, let's say, 1% of the Eddington limit. That can be anything, you know, between 0 or let's say below 10 to the minus 10 to, you know, anything, below the limit where we would classify these states. You have the, we call it a quiescent or low hard state. We see these states in both black hole XRBs and AGN. In the black hole XRBs, we in fact see accretion systems transitioning through these states. AGN, it might happen in AGN, but probably not on our, not during our lifetime, just because the time scale is so much longer. As interesting as these states are themselves, they are also important because, in the luminous states, they might be potentially less common than the quiescent state, but the energy they swallow and eject can be like many orders of magnitude more. So actually most gas in black holes seems to potentially fall into the black hole in these luminous states. If we look, though, how well we understand all these accretion states, we essentially find that only the quiescent state is relatively well understood, among others, because of a large simulation, community-wide simulation, library, repository, or what you would call it, of GRMHD simulations that can tackle them well. But in the hard intermediate and the high soft state, the numerical work is very scarce. It's they are very interesting, but it's extremely hard to resolve the razor-thin accretion disks that form when the accretion rate goes up and the plasma starts to cool down. That becomes extremely and prohibitively expensive. To understand accretion in these luminous accretion states, I've developed, I think it's now for the last decade, a new GRMHD code called HAMMER that can both address the physics, so both the ideal GRMHD equations, but also radiation, and last but not least, to temperature physics, because as we know, in many systems, electrons and ions have different temperatures, so it's important to evolve both the temperature of the electrons as well as the temperature of the ions, and of course also the Coulomb collisions that can equilibrate their temperatures, or the radiation that can cool the electrons. HAMMER features adaptive mesh refinement, many advanced features also, like local adaptive time stepping. Here you see an example of a HAMMER simulation where we essentially use AMR to zoom in on a razor-thin accretion disks. HAMMER scales now easily up to thousands of GPUs on the largest clusters in the US. And all of this numerical work essentially gives us the capability to really resolve and simulate these razor-thin accretion disks in these luminous, in the hard intermediate and the high soft state. In these states, we can see speed ups just because of the resolution exceeding a factor of 100,000 versus just the baseline. So a GRMHD code without any of these features. Still, even in the lower luminosity states, HAMMER still gives a reasonable factor 100 speed up. So the first problem I want to talk about that's really seen in these luminous accretion disks are quasi-periodic oscillations. They are essentially oscillations in the light burst. We see them in different categories, both at low frequencies and at high frequencies. Bottom line is no one really knows what they are or what they are produced. They were not seen yet self-consistently in GRMHD simulation. So why, if the GRMHD simulations don't show something fundamental we see in observations, why would we trust anything else that these GRMHD simulations predict? Well, the good news is the good news is that accretion disks which are misaligned with the black, which are spinning in a different direction than the black hole axis is spinning, were not really simulated. So that's what I've been busy with, let's say, up until maybe 1 or 2 years ago. Primarily tilted accretion disks. Here you see an accretion disk in the high soft state, accreting at approximately a few percent of the Eddington limit. That's tilted by 65 degrees. If I start running the simulation, you see, on the right, you see a contour plot of the density. This is just a volume rendering of the density. Initially, you didn't see anything, but as the simulation progressed, this is not going well, but I will solve it. Yes. So as you see, the accretion disk, the accretion disk tears apart into an accretion disk, which is very slowly or not. It shouldn't be precessing. It's just because I didn't know this would happen, so I chose an accretion disk which was also only 80 gravitational radii in size, but that later, and then accretion disk, which is precessing, and that's nice because precession can potentially induce such quasi-periodic oscillations. I'm not going to talk about that and move on to the next problem, which was partially mentioned in Ricardo's talk. Besides, let's say, slowly varying QPOs, we also have rapidly occurring QPEs, quasi-periodic eruptions, and of course we also have changing look AGN, which change their luminosity and spectral shape on time scales that just can't be explained by viscous processes in accretion disks. If we look at such a simulation that, let's say, accretes at maybe 10 to 35% of the Eddington limit is tilted by 65 degrees, and this time really includes self-consistent radiation and 2-temperature physics. That's what we have here. If we look at the vertical projection, then we see that there are some interesting things happening. The most interesting of those are that we see shocks forming. So we see, I call it a tearing shock. So a tearing shock essentially occurs when gas falls from the outer disk on the inner rapidly precessing disk. It needs to undergo a rapid orbital plane change, and during that it dissipates a lot of energy and heats up. This is, by the way, this is the electron temperature and this is the ion temperature. These are just the surface density and the scale height. But then there is also a nozzle shock, which essentially happens at the point where the disk midplane reaches the lowest or the highest point above or below the equatorial plane of the spinning black hole. And this is essentially induced by scale height oscillation. So you can see as you go around the disk that the scale height increases, decreases, increases, decreases. That's what's happening, and that's also causing shock dissipation. If we look at these nozzle shocks, that's essentially what an amazing student I've worked with has done, who definitely will be applying for the fellowship this year. What he has done, so he has essentially looked at the dissipation that happens in this nozzle shock. This is just a plot of the density along the azimuthal direction of the accretion disk, and he has just tracked the entropy and looked at the dissipation and found that approximately every orbital period, a few percent of the orbital energy gets dissipated in the nozzle shock. When you compare this, let's say, when you compare the viscosity induced by this nozzle shock to the viscosity induced, for example, by MRI turbulence, you find that the nozzle shock induces way more, like 2 to 3 orders of magnitude more dissipation than normal MRI turbulence. And just because the viscosity is so much higher, the time scale is so much lower on which variability happens, and also the amplitude of the variability is larger. So both the amplitude and the time scale actually of the variability matches really well of what we find in changing loop AGN. So this could be in addition to an orbital, to another black hole, kind of piercing to an accretion disk, maybe be an alternative model for changing loop AGN and QPs. So this is primarily what I've done in the past. What I'm now most working on is not only explaining the physics in these states, but also modeling the transitions between the states. For example, here you see a numerical simulation where I start an accretion disk. Oops, why is the animation stopping? This, yeah, that's unfortunate, but okay. I don't know why is that. Might be something with the animation, but okay. Bottom line is we are now really focused on simulating the transitions between the state, and this was supposed to show the transition from a quiescent state disk to a very thin and cold thin accretion disk in the half intermediate state. And yes, and this was some bonus slide anyway. So this is the summary.
Thanks for the cool talk. Are your simulations able to sustain super Eddington accretion for any meaningful amount of time?
That's actually a really important question, which a student of mine is addressing. Because yes, the problem is yes, simulations are able to sustain super Eddington accretion, but you would expect, radiative feedback to take place, and this radiative feedback, would suppress the accretion rate. And then, there are two scenarios. This radiative feedback will suppress the accretion rate indefinitely, or you would just have episodes of super Eddington, that you would have an oscillatory pattern between super Eddington and non-super Eddington accretion. And that's something we are trying, which is a very interesting question that I am working on. So, yes.
If we do not have any more questions, then let's thank all our speakers again.
Great.
Okay, so there are no announcements, so we will adjourn in and return.
11:35. Especially if you have been.
Yeah, thank you.
Next talk now, and for this we have a recorded talk from ZJ Zhang, UC Santa Cruz. And ZJ should also be there for questions at the end. So we're going to hear now about the chemical composition of self-luminous exoplanets and their host stars.
Hello everyone, I'm Zhi Zhang, currently entering the third year of my second fellowship at UC Santa Cruz. Starting from the summer next year, I'll be joining the University of Rochester as an assistant professor. So I will say I would really appreciate to be part of this program over the past 2 years and get to know many of you. And special thanks to Dr. Angelino for all your support and for answering my questions along the way. So today I'm going to talk about luminous exoplanets and see what we can learn from their atmospheres and formation. So here I'm showing a pretty popular diagram in the field of exoplanets. The y-axis is the planet mass, and the x is the orbital diameter axis. To date, we have found nearly 5,000 planets, and they are shown in gray. Question about how many planets have the observed spectroscopy, then these color symbols can answer our questions. So the objects in orange are those with transmission spectra, and the objects in blue are those with thermal emission spectra. So we can see most of the thermal emission spectra obtained for the objects in the top right corner of this diagram. So these objects have relatively far optical separations and high masses. So they are basically self-luminous gas-giant exoplanets that are typically found by direct imaging. So these objects are what my research is mainly interested in. So what we can learn by studying their thermal emission spectrum. So here I'm showing an example of James Webb data for the planet mass companion VHS 56b. As we can see, this data has pretty high quality, spanning a wide wavelength coverage, has a lot of features. So by studying this kind of thermal emission spectrum, we can learn or gain insights into the compositions of these planet atmospheres, including the abundances of water, methane, carbon monoxide, metals, or isotopics. So it is theorized that the planet atmosphere composition can be linked to their formation patterns. So in other words, if we study the planet compositions and compare that to the composition of host stars, we may be able to understand whether the planets form in the same way as stellar binaries or as through processes like co-accretion or distance doubling. However, computationally, it remains unknown whether this kind of connection between abundances and formation can be really established. So I think at this stage, it's really important for us to start collecting these abundance measurements and investigate the empirical trends among a large sample of planets in order to evaluate and establish this potentially very useful connection between the compositions and the formation. So inspired by this, I've been basically focusing on studying all of the spectra in the top right corner. So basically, I study the spectra of these planets and their host stars and measure their compositions. So in this talk, I would like to mainly focus on my analysis of two planetary systems, AI Lab and 2-7. So this my study about the AI Lab was briefly mentioned in the symposium last year. So this year, I will basically go through some main results quickly. So NHFP is a low-mass direct image exoplanet discovered last year. It was found by 3 groups around the same time. The planet is shown as a bright blob in this picture. It has a pretty low dynamical mass, around 3 gigatonnes. We collected all of the observational data published by those 3 discovery papers and updated the orbit of the planet, which is shown in blue. So in order to further understand how this planet forms, I first studied the properties of the host star, A. So I collected the optical spectrum with high resolution by using the Harlan J. Space telescope from the McDonald observation. So by studying this kind of stellar spectra, we can get a list of the stellar properties and also the stellar abundances, including the iron families. And then we study the planet. And here, the blue circles mark the observed spectrum of NHFP. So specifically, I characterize the planet spectra using atmospheric retrievals. So for all of you who do not do retrievals in your daily routine, basically, I hope this movie can explain how the retrievals work. So the retrievals are like playing the knobs that like each knob describes different part of the atmosphere. So one of the knob shown in the top right corner is called the PP profile. Another set of knobs in the lower bottom, right bottom, is describe the abundances of different molecules as a function of pressures or altitude. So we performed in the Bayesian framework, and it was exploring the parameter space until the predicted emission spectrum can match the data. So one novel development that we contributed as part of this work is that we designed a new approach to model the temperature pressure profile. So while the traditional method modeled the TP profile by directly fitting the temperature as a function of pressure, in our new work, we modeled the temperature pressure profile based on the temperature gradient. So there are more technical details behind this that I will not be able to cover given the time limit, but I will say like fitting the temperature pressure profile based on the temperature gradients allow us to break the degeneracy between the shape of the TP profile and the clouds of the self-luminous paths. So as a result, our method can help us to characterize the cloud problems for the cloudy self-luminous planets and black holes. So this method has been implemented in several recent studies using retrievals, and is also available as part of the direct transfer tool. So if you're interested in applying that for your favorite cloudy objects, please give it a try. Or I'm also happy to chat about this offline. So we basically applied this retrieval framework back to the AFLAB data. And what we found is the AFLAB likely has enhanced the atmospheric methodicity. So as compared to that of the host star. And in this conclusion, we basically run multiple atmospheric retrievals with different input of the planet spectroscopy and also with different choices of the pattern primes. And this conclusion about the macro enrichment of the AFLAB is also supported by some recent studies that either use horizontal analysis or that includes some kind of new observations from the James Webb for this remarkable planet. So the macro enrichment of the AFLAB combined with its low mass suggests that this planet is likely a product of the core accretion processes. And more recently, another interesting prospect of the AFLAB is like I found some evidence that this planet likely formed several million years after that of the host star. And this conclusion is derived by combining the mass luminosity of this planet by using the warm star thermal average models. And this analysis also helped us to constrain the post-formation entropy of this interesting planet. So more recently, I further expanded the analysis for the AFLAB to another remarkable system, which is 2MASS 1207. So the 2MASS 1207b, which is shown as a red blob in the picture, is actually the first rapid image and mass companion. It was first discovered by Gail Chabon back in 2004, and it has been instrumental in the field of rapid imaging of the planets because it helped us to understand the properties of the gas giant exoplanets. This year marks the 20th anniversary of the discovery for this remarkable planet. So the host star, 2MASS 1207a, is technically not a star, but rather a low mass brown dwarf. It is a member of the TW Hydra Association. It has a column of accretion emission lines, the optical and UV wavelengths, and also it has detected certain primary disk biology. And this kind of primary mass companion, 2MASS 1207b, has a mass of around 5 supermass. It has weak accretion lines, has no infrared access around 5 micron. So that means any disk contribution from this planetary companion will be toward the longer wavelengths. And this companion also has detected atmospheric variability, so that hints the atmosphere of this planet is likely homogeneous. So there's some new observational data for the planet, which is observed by James Webb years back. And this data are published by Luckman 2023 and Matt Backus 2024. And this kind of new data allow us to learn more about the planet atmosphere properties. So we can see here that the spectrum span a wide wavelength coverage, and also it has a pretty good quality. However, this new data has really provided some kind of challenges for the existing forward models. So in this diagram, the black is the change web data for 2-methylpsilocybin, which is downgraded to a spectral resolution of R100. And the red is the best fit animal forward models that is conducted by Lubman et al. 2023. So when forward models can fit the overall shape of the change web data, we can definitely see there's some kind of mismatch. So there's some offsets between data models in the near field wavelengths, and also the model predicts the methane absorption, which is absent in the observation. The models also predict much stronger CO absorption from 4.5 to 5 micron, which is stronger as compared to the observations. So these between model and data suggests that there still need a lot of detailed quality work for this near stack spectrum to better understand the pattern properties. So I have been basically applying the retrievals for the near stack data of 2-methylpsilocybin. And specifically, in order to account for the potentially complicated atmosphere of this companion, I have developed a new framework that accounts for the inhomogeneous atmospheres of this pattern and rock works. So basically, our framework can account for 3 different atmosphere schemes. So the first scheme is a popular one, which assumes the atmosphere is homogeneous with either cloud-free atmosphere or homogeneous clouds. And the second scheme accounts for the patchy clouds in the atmosphere. So where I use 2 columns that share the same TP profiles, but have different cloud properties. And the third scheme basically account for inhomogeneous thermal structure and also patchy clouds. So specifically, I have 2 columns that have different TP profiles and also have different cloud properties. So by running the retrievals with many different kind of setups, our goal is to learn like what kind of assumptions or setups can best approximate the near spec data of 2-methylpsilocybin. So with example results from our retrieval work. So this is a result when we assume the atmosphere of 2-methylpsilocybin is fully clouded, homogeneous, and we see like the model can fit the data pretty well, especially compared to the former models. But still, we see some kind of a mismatch between data and models. However, if we go to the patchy cloud scheme, we can see that the retrieval can fit the data really well. It basically can account for all of the features that we see from the observations. So this scenario tells us like around 90% of the atmosphere for 2-methylpsilocybin is covered by thick magnesium silicate clouds, and there are 10% that are thin cloud patches. So this kind of conclusion seems pretty straightforward. But to achieve these results, we basically tried out retrievals with more than 30 different setups. So it's really not trivial. Another takeaway from our extensive retrieval analysis is like, we see that as we're getting benefits, or when the delta BIC of the retrieval run is lower and lower, the inferred metallicity and the C2O start to converge. So that means like we should be always careful about the transitions derived from the retrieval with only one atmosphere set. So if you have the energy, definitely try out several different setups in order to better understand your favorite plans. And we are also studying the properties of the host star. So we have obtained the iris data from the 2-methylpsilocybin, and this kind of iris spectrum covers the K band, as I showed here. It has a pretty good form. And we extended the retrieval framework to the temperature regime of the late K and M stars so that we can now fit the iris data of the host star. So right now, I'm basically wrapping up the paper that describes the analysis for both planet and host star. So I hope like please do not circulate our results to the social media at the moment. Thank you. So I would say like I'm pretty looking forward in the coming years to expand the analysis that we have performed for AFFE and 2-methylpsilocybin to all of those objects with thermal emission spectrum in order to better understand the pattern formation on the population. So I will just stop here and ready for any of your questions. Thank you.
I'm afraid we don't have time for any questions for that talk, so we will pass straight over to Sarah Moran from NASA Goddard, who is now going to tell us about how clouds complicate everything. We're going to learn about neglected polymorphs of silicate clouds in substellar atmospheres.
Hi, everybody. I'm a first-year Sagan Fellow, so I just started at NASA Goddard 2 weeks ago. But I'm going to tell you about this project that really, I think, takes advantage of my strengths. I always say I'm like half a theorist and half experimentalist, and this project lives right in that middle zone. So if you walk away with nothing else from my talk, I hope that you'll retain this, that we can't ignore clouds because they are truly a fundamental part of any planetary atmosphere. That's true in our own solar system. I'm showing here that just to very first order to the human eye, the cloud patterns set what we see when we look out at these other planets. We extend that to thinking about not just planets, but even brown dwarfs. The color magnitude diagram I'm showing you here, a similar thing we think is happening is that as you evolve through color space, what you're actually seeing is the rise and fall of the clouds. So as you move down thinking about M dwarfs and these L dwarfs, you're getting redder and redder. And we think that's likely because silicate clouds are forming, reddening the spectrum. And then as we start to lose those clouds, as they sink below observable letters, we get bluer again. And then eventually you get cold enough that you get water clouds, and a similar thing happens. So not only are they by eye shaping what we see, but I want you to take away here that they're actually tracing out physics and chemistry for us. So these really powerful little probes of what is going on in the atmosphere. And so in this cartoon, you're seeing just at the most basic level as a function of temperature, that you're getting different cloud species and ultimately maybe even hazes, so it's photochemical products that evolve with temperature. And the idea of silicate clouds that you just heard a lot from ZJ about has been in the literature for a really long time, just based on thermochemical equilibrium. You would expect these silicate species to be present. And we've heard a lot about dust in the last couple of days, and that's essentially what these are, just dust clouds in these atmospheres. So I highlight here that the thing you hear about by far the most in both the brown dwarf and the exohot Jupiter literature is magnesium silicate. We expect them to dominate. If you go a little hotter, maybe you start getting other sorts of calcium silicates, but we have seen less evidence for that so far. And so that was known theory for a very long time. It was only with cryogenic Spitzer that we were able to actually observationally confirm this. So that big giant absorption feature right there is actually the signature of those silicate bonds that we're able to pull out. And you can actually go one step further and say, okay, it's not just the composition that matters, but the particle structure. And so what you're seeing here is the difference between amorphous or glassy particles and then crystalline particles. Just the way that they shape the absorption spectrum is you get this very nice smooth feature that comes from an amorphous cloud particle, and then these very spiky little things that might come from crystalline. If you move thinking to about hot Jupiters, we see evidence for a similar sort of trend. So what you should be reading here is that as a function of temperature, you're looking at the strength of the water feature as probed by the Hubble's RISC-3 instrument. And so you see this spike, and you think that's maybe a clear region of parameter space, and then you start to weaken that feature down through here. And I think that's again because of these silicate clouds dominating what we're seeing. And the reason we think that happens is just because by cloud mass, that is the temperature regime highlighted in that green box there, where these silicate clouds just really readily want to form and take up a lot of space in the atmosphere. The other reason that happens is because it's just really easy to start making these kinds of clouds. The nucleation rate of these particles, where they're transforming from vapor into a solid as a function of temperature, you can see that that orange line that represents forsterite, magnesium silicate, is just much higher than a lot of those other species. It's very abundant in the atmosphere, and it should very readily transform into cloud particles. Unfortunately, although this idea existed, we saw that sort of tentative hint from the Hubble with C3 data, we couldn't actually go as we had with Spitzer to go pinpoint the source of that absorption. And so this paper from 2015 highlighted that once we had JWST, we could go after the identity of the cloud particles in hot Jupiters again, because of this swapping feature that should pop out of the transmission spectrum. We couldn't do it anymore in Spitzer, so we lost that longer wavelength coverage. And in the meantime, everything we've heard about in the last, well, from CJ's talk and everything I've talked about has been very focused on magnesium silicates, because again, from thermal chemistry, that's what we expect the dominant species to be. So this paper that came out in 2021, highlighting here, that's the silicate absorption band from the spectrum. The best fit actually required not just magnesium silicates, but this additional contribution from SiO2 or silica. And I threw a whole host of different models of this, and it just turned out that you really needed this SiO2 in addition. And the only way you can start to add that into the spectrum is if you change the chemistry just slightly. It turns out that if your system, in this case, if the groundwork is the system as a whole, or if you have a planet, being the host star, has a different magnesium to silica ratio, you start to transition to getting more and more silica as compared to magnesium silica. Then, this was by far my favorite discovery of the last year, is that with JWC's Miri, we finally delivered on that promise of being able to identify the cloud species in a hot Jupiter. And so highlighted right there is the absorption that these authors were able to pinpoint as being due to silica clouds, not magnesium silicates. And they had no evidence for magnesium silicates, and just pure SiO2 here. You can also go a step further there, and so if you look at the rightmost plot, that difference between the yellow and the black there is what you'd expect the difference in that peak to come from either amorphous glassy particles or crystalline particles. And then you can also see that you can probe the size distribution of the particles in the atmosphere here on the left, that you start to change the strength and the shape of the spectrum as a whole, just purely based on the cloud particle size distribution. And I should say that this tension between whether the particles are amorphous or silicon is also telling us something about the physics of how these things are forming. You would expect amorphous particles to be present if you initially had your nucleation, and you immediately pull that particle down very, very quickly. Whereas if you're having these particles persist at these high temperatures, you'd expect them to be in a crystalline state. And so the fact that we kept seeing amorphous signatures when we expect the atmosphere to be very hot was confusing and perplexing for a theorist. So this made me really happy that this seems to be crystalline, because it's what we would expect. And so this has all really just been built up to my project, is like, I hope from this you've seen that clouds are this very powerful tool that we can use to understand the atmosphere as a whole, and think about not just the chemistry, not just the particle structure, but you can actually go one step further. And so that was what I did, and I went way, way down into the weeds of how particles look in order to do this project. And so it's not just a matter of whether these particles are amorphous or crystalline, but it turns out there are many different types of crystals you can make. So this is just an example showing for silica the different atomic stacking arrangements you get in these different kinds of crystals. And I'm highlighting here, this is a phase diagram that you might see in like a geology talk. And so all the different phases you get of all these different crystalline forms. Of course, I don't care about anything up there. I care about this tiny slice at the bottom. I would actually prefer that the y-axis goes significantly lower, but that doesn't really exist because geologists don't care about that. And so this motivated me to look at, okay, what does this mean for hot Jupiter atmospheres or groundwork atmospheres? And so the key here, you're seeing the different phases here, the two different forms of quartz. And tritonite and crystallonated, these forms of silica that we might expect. And so now you're looking again at a sense of temperature pressure diagrams for various atmospheres. So we've got WA 17, which is where that quartz detection was in that I just showed you. WASP 107b, which you'll hear about later, and that something sort of similar to the Eldor for that silicose emission we found. And that's what those solid lines are. The dotted lines are the condensation curves of where we would expect that transformation to happen. So anytime that the corresponding colors cross, like I'm highlighting here with these little cloud cartoons, that's where we expect cloud formation to initiate. So in these different highlighted regions in the background shows you the dominant form of what crystal phase you would expect at what particular temperature. And because these crystals are different, here I'm just showing you a pretty picture highlighting how they look different, you would expect their spectra to also look different. Their refractive indices differ very slightly, their densities differ very slightly, and when we're thinking about cloud modeling, these are the things that matter, right? These are the things that set what is observationally able to be pulled out. And so this project was asking the question, are these little differences between the different kinds of crystalline phases observable? And so to do that, I use these set of open source tools. Verba is the cloud module, and Caso is the radiative transfer finite chemistry module. And so I was able to build up a set of optical properties for these materials. I have this highlight here because it seemed like it would be trivial to me, and it turns out that was what took the bulk of my time in this project, and I'm happy to chat or rant to you about why. So we had this data, so we then run a me code to actually get values to be able to input into the cloud code, and even just by eye here, you can see that the spike of this absorption feature does differ between the phases. So the next question is, what does that mean if you actually involve that with an atmosphere? And so I'm just highlighting here the cristabolite, which is the pink model here, everything else being equal, just changing the optical properties. The cristabolite is actually a better fit to the data than quartz, which is encouraging, right? Because at these temperatures, that's the form we would expect it to be in. We look at tridymite, which is a slightly lower temperature crystalline phase. It doesn't fit particularly well, but part of that I think is not real. I think it's because of the rant that I haven't given you about the state of the lab data I had to use to make the model run. So I don't trust this region right here, which of course is exactly what's driving that bad model. So I also accounted for the density differences between these crystalline phases. It turns out that doesn't make a very big difference. So like the dotted lines versus the solid lines, which maybe if you squint, you can see from there the differences. You do get a slightly better fit if you account for the right density, but it's not statistically meaningful based on the gain you get versus the penalization of adding more parameters to your model. And the reason that's happening is because you're just not making a big enough difference in your density to drastically change the particle size distribution. So this is showing you the mean particle radius as a function of pressure, so the difference between these phases is like a couple of nanometers, which is not enough to make a big difference in your observation spectrum. I applied this to ground dwarfs as well, and this also should be observable. I am out of time, and so I'm going to fly through this. You can do a little fun thought exercise where you ask, can we predict the cloud particle that should exist? So if we do this for WASP 107b, you can imagine how long does it take to have that particle rise. You can do a little back of the envelope math and find out that if you spend enough time in each of these regimes, will perhaps have multiple different crystal phases at the same time, which I think could actually be solving some of the amorphous versus crystalline tension, is that maybe you're just seeing mixed phases that blend out those very fine structure features. I think this is important for a whole bunch of other things that I'm trying to tell you about. And so I'll just leave you with my takeaways that if nothing else, clouds are important traces of physics and chemistry, and we can get really into the weeds to pull out some really crucial information about atmospheres and how they work just based on the clouds alone. Thank you.
We have time for one very quick question. What?
Thank you. I wanted to ask about the mean code they were using. My understanding is that mean code usually, or the mean approximation assumes a spherical geometry, and these are crystalline structures. So I was wondering, does that impact the analysis at all?
So the question was, I'm using mean theory to calculate my optical properties, but if they're crystalline, how can they be spheres? And yes, the answer is I did pretend they were spheres, and that should not be true. And my very next thing to follow up on this is to do that properly, but it's still a work in progress.
Okay, thank you again, Sarah. Energy is high for a talk now, pushing into the high energies for the near UV transmission spectrum of LTT 9779B. Take it away.
Thank you for amping that up, and also thank you, Raphael, for setting up this talk.
for what is undoubtedly going to be a huge anticlimax. You'll see why in a little minute. Yeah, so this project, I'd just like to call out some of my collaborators, Antonio Koch, faculty at the University of Amsterdam, and Dion Linson, my main two collaborators. Also, he's a grad student just finishing up there, and my mentor, Heather Knutson here at Caltech. Yeah, I'd like to thank you so much for the help on this project. This is the last talk. Well done, everybody. You made it. And as a reward, I think we should just take a little minute to enjoy some beautiful music. Don't worry, I'm not singing again. Those of you who were at the open mic last night have definitely had enough of my singing, but thank you for also returning for this second performance. Instead, I think we should enjoy the sound of exoplanet discovery. So in the last 30 years, we've found over 5,000 planets around other stars, mainly from large surveys like the Kepler Space Telescope, which focused on that purple patch in the sky right there. And this monumental human achievement is the culmination of very careful and very passionate work of thousands and thousands of people over actually thousands of years. And all of you in this room have contributed to that, even if you don't like exoplanets or work on them directly. Nice. Thanks for your. So we're trying to piece. Oh, I forgot to mention the tone of the sound that you heard in that music represents the orbital period of the planet, and the radius represents that size. So there's actually a lot of information about the population of planets that we know today in that graphic. However, for a lot of planets, that's kind of like all we know about them, the period and the radius. And we're collectively trying to piece together the story of planet formation and evolution from birth in the protoplanetary disk, which is shown as that dark band across this image of L1527b taken with JWST, and all throughout the planet's lifetime. Now, even when a planet is all grown up and fully formed, its atmosphere is a very dynamic place because it acts as the interface between the planet itself and the rest of space, which can be quite chaotic. So I focus mainly on mass loss. And this is a very complex process that happens, and there are loads of different physics that goes into atmospheric mass loss. We've got the proximity to the host star. So most of the planets that we've discovered are very close to their host stars. And they're very strongly affected by high stellar radiation, stellar winds, the magnetic fields of the stars and the planets, and also the composition of the planetary atmosphere itself has a big effect. And there's strong evidence to suggest that mass loss has played a very important role in sculpting the population of planets that we observe today. So we've got distance to the host star and planet radius here. Now these are all of the planets that were found orbiting close to their host stars. And we see quite a few planets up here, Jupiter-sized, and the easier ones to find. And we see a bunch of tiny ones down here, Earth-sized. And then we see kind of a dearth of very close-in planets of water around the size of Neptune. This is, as we've spoken about before, the hot Neptune desert. So these planets are easier to find than these tiny ones down here. So this is a real dearth of planets that we're seeing. And we don't see it look so much further out over here. We see more Neptune-sized planets over here. And we think that perhaps these planets have had their large voluminous atmospheres stripped away because they're so close to their host star. But this has kind of been difficult to actually really prove because atmospheric mass loss for exoplanets is a very difficult process to observe directly. So I'm trying to develop new ways to actually observe these processes happening. And to do that, I use the transit technique as a planet passes in front of the host star. And for atmospheric mass loss, we're really studying those very upper reaches of a planetary atmosphere. Now, these are very low density, rarefied regions that makes them especially difficult to study. And so we need to use very strong absorption lines to actually be able to see these things. For example, the Lyman alpha line, the jump between the ground state and the neutral state, ground state and the first excited state, neutral hydrogen. This was first used to detect a huge stream of atmosphere escaping from HT209 over 20 years ago now. This image here is actually the Earth, shown in Lyman alpha, but actually broadband UV wavelengths, which covers the Lyman alpha line, and also some strong oxygen lines actually that you see glowing in the aurora and sort of around the tropics. But the giant cloud, the halo that you see around this image is the Earth's atmosphere. That's hydrogen gradually trickling away about 3 kilograms per second. And you can see it's much larger than the planet itself. And so we use that to our advantage when we're looking for escaping atmospheres, which may be very extended. I'm going to talk about one planet in particular, LTT 9779b, which I have misspelled on this slide. This is a hot Neptune exoplanet. It's actually a very special, unique planet. Here it is within the hot Neptune desert. It is basically the hottest Neptune that we have, where we know it definitely has a large atmosphere. There are a couple planets nearby of it in this plot here, but those tend to have, those actually either don't have measured masses or they are much more dense. So this planet is essentially the same size as Neptune and is slightly less dense, but it has an equilibrium temperature of nearly 250,000 Kelvin. So it's extremely hot. And it's a mystery as to why it exists. We think that these planets here all they don't exist. They maybe start off here and then have their atmospheres stripped away and move down to become smaller planets here. It's confusing why this has survived so long in the hot Neptune desert, as it's a fairly old star. Some people have gone to look at evidence of atmospheric escape on this planet. Presumably it should be losing a lot of its atmosphere. People looked with Weinrad on the Magellan telescope. Mr. Pragada did that and looked for evidence of helium absorption, because helium is another powerful tracer of atmospheric escape, and saw nothing. Just as a reminder, this is what a strong detection of atmospheric escape in the helium line looks like. So it looks like this doesn't have a large gaseous envelope of hydrogen and helium escaping from the planet that we're able to detect. It may be because this star has a very low X-ray flux, which is measured by Jorge Fernandez et al. With XMM Newton. They posit that this star has actually an unusually low rotation rate. And this means, compared to other stars of its stellar type and age, so maybe this planet has continued to exist in the hot Neptune desert because it has an unusually low activity star, and it's just not undergoing substantial mass loss. Because this is such an outstanding target for transmission spectroscopy, it's been gone at with every telescope we have available, including JWST. And this is a transmission spectrum from Michael Radke et al. This year. And they see quite a flat spectrum. So this could be either because there are a lot of clouds in the upper atmosphere of this planet, or it also could be because it has a quite high metallicity. So, other more enriched in metals, which could squish down the planetary atmosphere. But we're actually unable to differentiate between these two scenarios with JWST right now. So I love to use Hubble still. It's a phenomenal companion to JWST. And I'm really getting into observing planets at UV wavelengths to see if we can see features in planetary atmospheres that are completely inaccessible with James Webb. And the lines that we're looking for in this program are magnesium and iron lines. So these are first detected with HST in the exoplanet WASP-121b by David Singh in 2019. And they showed a huge envelope of escaping material, which had very heavy metals. Even those are being dragged out into the upper atmosphere. And you can only detect these for very hot exoplanets. And LTT 9779b is the only planet smaller than a Jupiter size that we think we should be able to see metals in its upper atmosphere. I'd like to make the point here that even if it's not rapidly losing a lot of mass, we still may be able to detect metals if it has an extended upper atmosphere. Just like the picture of the Earth that I showed you in the beginning, we're only losing 3 grams. Wait, I forget how much we're losing. The Earth is only like trickling its hydrogen away. You can still see a very large extended cloud of material surrounding it. So even if we are not directly, the planet is not directly losing a lot of mass, we still hope that we should be able to see a lot of metals in its upper atmosphere. And so Dion Linson in Amsterdam, I spelled the planet name wrong again. Oh dear. He ran these, they have a super cool model he's been working on that is self-consistently able to predict the temperatures of these upper atmospheres, which is a kind of difficult thing to do in planetary mass loss model sphere right now. And he was able to predict that we should, in fact, be able to detect, hopefully, magnesium and iron in this planetary atmosphere with HST. The plot I'm about to show you is not a real spectrum. These are predicted observations from HST. So this is a program that was led by Antonia Oklopcic, and I was the co-PI. So this is kind of these are the kind of precision that we're hoping to see with HST, which has never been able to do before with the Neptune-sized planet. What we're hoping to do with these observations is to determine whether LTT 9779 has had all of these non-detections because it's cloudy, or does it have a metal-enriched atmosphere? We're hoping to use the strength of these absorption features to figure out just how metallic this planetary atmosphere is. I said this was an anticlimax because I actually do not have the observations to show you. I've learned a lot from this program. One of the things I've learned is that I should not use talks as motivation to finish my projects. I really thought that I would have the spectrum in time to show you, so I do apologize for that. Look out for it in the next few months, though. I'd also just like to end on a very big thank you so much. I cried when I received the email that I was awarded this fellowship, and it really changed my life. And I think it was an absolute huge factor in me being able to get the permanent job at Carnegie Observatories that I've just started last week. We're starting we even have already a small group of exoplanet folks there. So if you know any grad students who are interested in exoplanets and looking for postdocs, please recommend them to apply to Carnegie. We'd love to have them there. Thanks so much.
Hey, do we have one final question? Yes, Sarah.
You set up this sort of dichotomy between it's a it could be cloudy, it could be metal enriched. Is it possible to be both? Be able to see?
Yeah, for sure. If it's both, I think the strength of the metal lines might tell us something about that. Yeah, good question.
And do we have a closing speech? Okay.
You take that down.
I don't know if this is a speech, but anyway, okay, but we can. All right, so first of all, I want to say a big thank you. I think you all deserve a hand. You guys are all amazing. And I love this program, but I'll get back to that. Okay, so if you are still here and you were on the SOC, can you stand up one more time?